So let's practice applying the multiple server model on this example. So what do we have here? The service is a taxi service for a company that's stationed at the lower gate at LU. The company has determined that customers arrive at a rate of 5 per hour on average, and it follows a Poisson distribution. The duration time is 48 minutes, and this is very reasonable considering the traffic here in Lebanon. And we are assuming that one customer is per taxi, right? Which complies with the arrivals here. Because if two customers can go in the same taxi, then we have a problem with the arrivals. But this makes it very, very simple for us. And we need to determine some performance measures, which comes in the next slide. But before doing that, again, as usual, we need to answer 3 questions. What's lambda, what's mu, and what is m? Okay, so lambda is very clear in the second paragraph. It's 5 customers per hour. And also we pay attention always to the time unit. The service time is given as 48 minutes, which allows me to find the mu. And I'll multiply it as usual by 60 to make it in hours to comply with the time unit there. So that's 1.25 customers per hour. Okay, finally, I will determine my famous ratio, lambda over mu, because we're going to use it very often. So we get it 4. All right, so now we are ready to answer any question in the next slides. Okay, so let's start answering these questions. I put here lambda over mu so that we remember it. In all our calculations, we may use it. Also, we have a mu here and we have lambda. With the probability that all the taxis are idle. In fact, to answer this question, I'm going to refer to the table as we agreed. We're not going to use the complex formula. And the same for the LQ, right, which is in part B. So I'm going to do that. So let me show you the part of the table that includes the area where, or corresponding to lambda over mu equal to 4. So here we go. We said that you look in the table first to the corresponding lambda over mu that you have. And then within that area, you look at the right row. In our case, m is 5. So this is the first row. And we can easily read here, the first one is your LQ, so it's 2.216. I'm going to round it to 2 decimals, to 2.22. And this is P0, 0.013. So that's it. We simply read it from the table. All right. So here we go. We look in the table, we find P0, 0.013, and here we go. Okay. Now I can remove that table to answer the other questions. Let me just clean this up. All right. And now, see, find the average number of customers waiting and being transported. So this is LS, right? Because being transported means being served. So that means all the people in the system, LS is LQ plus lambda over mu. So that's 6.22 customers. Average time it takes a customer to get into a taxi from the time he arrives at the corner. What's that? So this is how much he waited in line, right? So that's WQ, which we know from the basic relationship to be equal to LQ over lambda. So that's 0.44 hours. You can leave it like that, or you can transform it to minutes. So that's almost 27 minutes. And now we're going to answer more questions. So 2 questions about the probability. Remember, in a multiple server, it's very important to know which formula to use because we have 2 formulas. The first question is find the probability that 7 customers are in the system. We know that m is equal to 5. So we're asking about a certain value of n which is greater than m. So we use the first formula, which is this one. Okay. So how to do that? Lambda over mu, we have it 4, and m is 5, so 5 factorial times 5. So this part can be tricky a little bit for some students, so make sure that you practice enough. M is 5 to the power n, which is 7, right? Which is the question here. Minus 2, so it's 5 to the power 5 here. And don't forget to multiply by P0. This is also a common mistake. Students get too much involved in finding this that they forget to multiply their answers here by P0. Doing that, you get 0.071. With the probability that 4 customers, okay, are in the system. So here we have n smaller than m, so which means I use the simpler formula. Plugging the figures, we get P4 to be 13.87%. Now in part G, the question is find the probability that 2 customers are waiting in line, or they are waiting for a taxi, meaning that they are waiting in line. So obviously this is not simply P2, right? Because Pn is the number of customers in the system, and this is not the question. The question is P2 in line. So as we did before, we need to convert that to make it in the system. So this is an illustration for the system that we have here. We have 5 taxis, and this is why we have here 5 squares, each one representing a server. Okay, so we have these, each one of these is a taxi. So we have 5. So the question is, 2 customers are waiting in line. So here we go, they are here waiting in line. Why they are waiting in line? Because all the taxis are busy. Busy with whom? Busy with other customers. So I have 5 other customers, I know that. When I have 2 in line, that means I have 5 being served, which means the total in the system is 7. So that allows me then to write this equivalence, right? P of n equal 2 in line is P of n equals 7 in the system. And this is an answer that we found in the previous slide, which is 0.071. Last question, find the probability that an arriving customer will have to wait. Again, imagine yourself arriving to the corner here. You are arriving, you're wondering, what's the probability that I will wait? So you imagine the system inside. If you arrive and there are 5, if there are 4, for example, you don't wait, right? You go directly to the idle taxi. But if there are 5, you will wait. So you wait if there are 5, so that's P5. But this is not the only case. You may find someone else waiting in front. Okay, so you wait behind him. So you will be waiting if there is also 1 waiting in line, that means 6 in the system. Or 2 in line, that means 7 in system. Or 3 in line, that means 8 in system. So PW are all these probabilities, or the sum of all these probabilities. So to do a more concise calculations, I'm going to find the complement of these, which is 1 minus the probability of the other cases, which is 0, 1, 2, 3, and 4. So I need to find these. Okay, so I'm not showing you how to do it because you should be familiar now how to do that. Okay, P0 we got it from the table, and P1, P2 I think no, we did not get it, but P1, P2, P3, P4 you find it using we found P4 previously, and you find now P1, P2, P3 using also the simpler formula, the simpler probability formula, because all these cases have n smaller than capital M, which is 5. And this will be our final answer. So we will have almost 55% chance that we will have to wait. Okay, so I hope that this problem was clear enough. It illustrates the use of the multiple server, which is a widely used model for obvious reason, because most service systems have multiple servers.